In 10.4, we're looking at areas again, but this time we're looking at areas that are defined by polar equations. And the formula for this is pretty different from the formula for areas defined by Cartesian equations. And this is all based off of circles. So take a look at this. The area of a circle we know is pi r squared. This is actually a special case of this formula that's going to be used for areas of polar curves. Let's look at this. If you've got a circle and you draw in a central angle, and the angle's theta and your radius is r, if you want to compute this area here, it's given to you by this formula up here. The area of that sector is 1/2 pi r, or 1/2 r squared theta. Now, if you take your theta to be the entire circle, then that would give you the area of the full circle. And plugging into there would give you 1/2 r squared. Theta in this case is 2 pi. So that would give you pi r squared. So that's what we're going to use when we develop something that'll let us find the area of something like this. All right, let's erase this and then look at that. All right, so we want to find the area of this. Remember, r is f of theta, so the radius here, the distance of any point on this curve, the distance from the origin, is a function of the angle theta. And so it's, moving around like this. So the idea is, let's take this and split it into a bunch of really small sectors. So we take a bunch of sectors here, and we treat each one like it's the sector of a circle. So maybe, we have stuff that looks like this. So if we took this angle here and we picked either this radius on top or this radius on bottom, we could use that to approximate the area inside of here. And of course, we're going to get some error because those two radiuses, they're not exactly the same. So let me erase those. The idea is we use a whole bunch of these. We shrink these angles all down to essentially 0. And then we'll be able to add that sum up and come up with the area, the exact area. Now when we do that, the angle in here shrinks down to nothing. So it's like d theta. And then we pick a point here, here, or here. It doesn't really matter. But we pick that, and that's our f of theta. So the area of, say, just this one sector, the area is going to be 1/2 r squared theta. But for this particular sector, our r is f of theta, and our d theta, our little angle is just, or our theta is d theta. So the idea is we integrate this from the start to the end, and that gives us the area inside of that curve. Now I want to do some examples where we find this. But before we, or some examples where we find areas, but before we do that, I want to talk a bit about Rose curves. Let's talk about those, and then we'll do some examples. Now, a Rose curve, I'm just going to pull it up on Desmos here. Rose curves have this form, either r equals sine theta or r equals cosine theta, possibly with the coefficient on the front of the theta. So if I come over here to Desmos and I type that in, if I put in r equals sine theta, we get this little circle here. Let me drag it up here so we can see it. Now, if I put a coefficient on the front of that, say a 2, we get 4 lobes on the thing. 4 lobes or petals. That's the reason they call them rose curves, because it looks kind of like a flower. So there's a 2. If I put in a 4 here, we get 8 petals. If I put in a 6, we get 12 petals. So anytime you put in an even number, you get twice that many petals. So there's one with 200 petals and it's all smushed together. There's one with 20 petals. If you put in an odd number though, you get that number of petals. So in this case, 1 gives us 1, 3 gives us 3, 5 gives us 5, and so on. Now all the ones I've done so far have been with sine. If you put in cosine, it's like it rotates it so that the starting lobe over here lies right on the axis, whereas with sine, the starting lobe points upward, goes upward over there. Now, why is that the case? Well, let's look at sine 2 theta. If I were to graph y equals sine 2 theta in sort of the normal sense, it's going to look like this. We're going to have this area, we're going to have this part here from 0 to pi over 2. And then we have this part from pi over 2 to pi. So let's go back and just restrict this to just 0 to pi over 2. That gets us that first lobe. And if you think about what's happening here, as we go around this graph, we start out with the radius of 0. The radius grows up here to the radius is 1. Then it shrinks back down to 0 again. That's exactly what happens here. It goes from 0 to 1 and back to 0. Now, this is easier to see on a different Desmos sheet. This is one I've got where I've got things animated where you can see things. So in this case, I've got r equals sine 2t, t instead of theta. But with my b here, if you trace what's happening here, if my b goes from, as it goes from 0 to, there it is at pi over 4, but then pi over 2 is like 1.57, it gets back down there. And now if you look, the next thing it does is it goes into quadrant 4, and traces out that lobe. The reason for that is over here, if I were to draw some dotted lines here, so this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. As we go in quadrant 2, that's from pi over 2 to pi. So that's like over here, this section. The radius is negative, which means it's going to give us something out over here. And that's the reason from pi over 2 to pi, it goes through the third quadrant. I'm sorry, the fourth quadrant. Then it's going to go through the third and then through the second. So we can watch that, see it animated. And if I change this to a cosine instead of a sine, it's going to be the same shape, but it's rotated a bit. And if you look at it, we start here at that 1. And the reason for that is graphing cosine 2 theta looks like this. That's pi. That's 2 pi. So when you go from an angle of 0 to an angle of pi over 2, 90 degrees, going from the x-axis up to the y-axis, we're going to go, the radius is going to shrink from 0 down to, or from 1 down to 0 to -1. And it traces things out like that. So we're going to look at finding areas of these petals of the rose curves. We'll look at that in the next video.